Questions? Let me shut off that projector. Hopefully it's up. Any questions about anything? All right, so last time we talked about how to get the actual, from a fundamental standpoint of the magnetic vector potential, how to derive the B field, and from the B field to get the E field from a short dipole. So we did short dipole, and really, just to bring everything into context, when you have a short dipole, that assumes the length of the antenna, L, is going to be less than lambda over 10. That's what I say. All right, it's going to say much less than L in the book. Well, lambda over 10. I mean, it's going to say the length has to be much less than lambda, really just less than lambda over 10, a tenth of a wavelength or less. All right, so that's a short dipole. From that, if this has a current I naught here, these are the characteristics. First thing, there's three things really we get from that right off the bat. We could get the magnetic vector potential A and then get B and get E, right? We could go through that derivation. We only do that once. I already did that. Now what's left is the E field. That's the thing you focus on. And we can get the H field from the E field easily. So the actual electric field from this, and this assumes it's oriented in the Z-axis, right? It assumes that there's an angle measured from the Z-axis to the radius vector r of theta, and it assumes that the E field, and for this case it's in the far field, the E field itself will be equal to, so this is far field 2. And by the way, what's the far field? I mean, in your own words, what is it? Not the equation. What's the difference between being in the near field or far field? Anyone? There's no, all the energy is propagating, right? You're talking about no measurable or appreciable amount of magnetostatic or electrostatic energy. Do you follow me? This is fields that are launched for good. So from there we get, it's equal to J eta beta, right, times I naught, right, times the length of the antenna L over 4 pi r, that's the radial distance. The angular variation is sine of theta, and it's in the A theta direction. That's the E field. The H field you can get, really, since we're talking about far field, E cross H is the direction of propagation, right? Well, if that's in the theta direction, the H field would have to be in the phi direction in order for it to be propagating radially. So H you really get by just taking this E field, take E theta and divide it by eta and put it in the A phi direction. So if I divide that by 80, you can see it's just J, right? And then it's beta times I naught over 4 pi r times L times the sine of theta in the A phi direction. That's the H field. Next thing you can get is the total power radiated. Now remember, the way you can get it is, to get the total power radiated, first you need the average power density, and P-av for this one is really going to be 1/2 the real part of E cross H conjugated. Now that's the formal way to do it. Do you remember what it comes down to in terms of the E field or H field? Anybody? Well, what's going to happen here, this is the real part of that number, is it's going to be equal to 1/2 the actual 1/2 the magnitude of the E field squared over eta in the AR direction. And it's also equal to 1/2 times, and then it would be just the magnitude of the H field squared times eta in the AR direction. Either one of these two is correct, because E is equal to, in magnitude, H times eta, if you look at that. Follow me, class? So all those are the same. Now, if you do this, the actual radiated power density, if we did this one right here, right, we'd see that P-av would be equal to 1 over 2 eta naught. This would be in free space. And I got to square all this stuff. So then I have, this stuff. I have eta, beta, I naught, L over 4 pi right? Time all that squared, sine squared of theta, and I have divided by r squared, and it's in the AR direction. Now, that would be the power density. One thing you're going to see is the eta naught here will cancel one of these etas, so you're left with just one eta up top. But that's fundamentally it. Follow me, class? You'll notice it's proportional to I squared, it's inversely proportional to R squared, and it's also proportional to the sine of the angle squared. Now that's the power density in watts per meter squared. This is in Wentworth's book. We can reduce this, and I'll tell you a lot of things happen right here if you want to reduce it. First, the eta naught cancels one of those eta squares, right? So you just have eta here. Then beta is 2 pi over lambda. A lot of times that 2 pi over 4 pi is just 1/2. Follow me? So you're going to have 1/2 lambda, 1/2 over lambda. Then they group L over lambda, so it's a ratio of length over lambda squared. And they can keep on reducing that. But this is the essence. This is the thing you need to know. That's what it is. Now, the total power radiated, right? P radiated from a short dipole would be, you would be required to go from 0 to 2 pi, from 0 to pi. This is a review, by the way. We did all this already. I'm bringing up the speed so I can go to where I'm going today. Then it would be this, P av, right, as a function of theta, phi, and r. Then it's times r squared times sine theta d phi. When all is said and done, we find out that this thing is equal to, and I'm not going to do this integral again, because it's really the sine cubed integration, where we break sine cubed into sine squared times sine theta. Let sine squared be equal to 1 minus cosine theta, and then remember how we did that integration? That's what it breaks into. But after you do this whole thing, you're going to see this. It becomes 40 pi squared, all right, times I naught squared, and then it's going to be times L over lambda squared. Now he has this in his book. If you if you have your book, look at the total power radiated from a short dipole. Yep, and it's 40 pi squared L over lambda times I, lambda squared times I squared. This is it. What equation is that, by the way? 444.
Oh, it's, yeah, 855 on page 4.
8.55? That's the equation number. Now, this is equal to, and this is important, this is equal to 1/2 times I naught squared times the radiation resistance of the antenna. Remember, the radiation resistance is the thing you need to know to figure out how much power is radiated if you have a current going through there. Everybody with me on that? That will be key, and you will be tested on this, and it's coming up. What is the radiation resistance, therefore? I'll put it right here. Radiation resistance would be equal to 80, right, pi squared times L over lambda squared. Now you would like that number big, but for a short dipole, it's not big. Let's see where the limit is. If we are right at the verge where it is short, where it's lambda over 10, take a look at this. This is going to be 80 pi squared. This would be 1/10, right? 1/10 squared is 1/100th. So that would be 0.8 pi squared. And didn't we do this last time? On Friday, didn't I ask you what that number was? Do you remember? No. I thought I asked that. Maybe I didn't. All right, what I'm trying to do is show you how bad a short dipole is. So if we take the limit where the length of the antenna is lambda over 10, then I get R rad, which you would like to be big, is not so big. Now that's equal to what? 80 pi squared times 1 over 10 squared. And that's in ohms. That's going to be 0.8 pi squared. What is that? Well, pi squared is about what? 9.5, 10, right? Huh? I'm sorry. We're less than 10 ohms there, right? I should say, maybe I'm wrong, but it's around 10 ohms. Has anybody got a calc? What? 8 ohms. 8 ohms is extremely small, all right, for an antenna's impedance. Because now that means when you put current through there, remember you're going to get losses due to the dissipation. At high frequencies, they can be appreciable, well over 8 ohms. You're going to dissipate most of your power with that kind of thing at a short dipole. I shouldn't say absolutely, but usually if you're at high frequencies at least, this is a very low resistance. You would like it much, much higher. All right? One other thing we did too about this, first we got directivity, and if we knew the efficiency, then we could get the gain. For the directivity, do you remember how we got directivity max? People, I want to do this, make sure everybody's got that. Anybody? Very good. 4 pi, right? And it's over something called the solid angle. In Dr. Whitmore's book, he uses this, the solid angle. And that is of the form of a double integral, right? From 0 to 2 pi, from 0 to pi, of the normalized power density. Now, this is the thing I was bringing out last time. This equation is the power density, right? Normalized power density means when you divide this thing by the maximum value it can have, you get the normalized power density. Does everybody recall that? Well, the largest value this thing could have is when sine of theta is equal to 1, right? So you would divide this thing by everything but sine of theta, follow me? And you would be left with sine squared. So the normalized power density for that antenna would be sine squared of theta. So you put in sine squared theta. Then you put in times the solid angle, which is the sine of theta, d theta, d phi. Everybody remember doing this? We did this, right? I really was trying to emphasize why it means what it means. That's the solid angle that goes here that gives us the directivity max. Now, I want to make sure everybody sees this. You remember this becomes a sine squared becomes 1 minus cosine squared, right? Everybody remember that? We do the integration. After the integration, this is 8. What? It's 8 pi over 3, correct, class? That's 8 pi over 3. You stick that into here, this becomes simply 3/2. The directivity of a short dipole maximum is 3/2, or 1.5. Everybody with me on that? Now that just says how much better it is than an isotropic radiator for focusing power. It's just a little bit better. Right, an isotropic radiator would have a directivity of 1. So this is 1.5. You're not buying a lot. All right? You're not getting a lot of focusing power. But you're getting some. It's 1.5, or 3/2 is the directivity max. The actual directivity in any direction as a function of theta or phi would be equal to the maximum value times the normalized power pattern. In our case, it would be equal to simply 3/2 times the sine squared of theta. It's sine squared of theta, and that would be d as a function of angle. Remember, it's the normalized power. Power is sine squared. Follow me on this, class? All right, now, hear me. That right there is almost what we really want, but what we really want was the gain, and that depends on the dissipative resistance, all right? Which means you also have to know the frequency of operation, because remember, the higher the frequency of operation, the more the current clings to the surface, right? And the higher your resistance. Do you all remember that? That would be the loss resistance. How many do? I want to make sure I'm talking to the right crowd. You remember how what we talked about RAC, or high frequency, where it's much higher than just the DC resistance of the wire because the surface only has the area of one skin depth to run through, right? Everybody with me on that? That's what you'd use for the dissipation. Anyway, what you'd find is this. You would get the efficiency be equal to simply R radiation, which we have as this, R radiation is 80 pi times length over lambda squared, right? And it would be R radiation over R radiation plus R dissipation. That would be the AC resistance of the antenna. Clear on this, everyone? I'm going through the whole thing with you. Make sure you get it. Once I have that, I can get the gain, and the gain is just going to be the efficiency, right, times the directivity as a function of theta and phi. Now, I didn't give you a specific frequency in this thing, but for any given frequency, if you know the actual length of the antenna, right, you can get length divided by lambda. Follow me? Now you have that, square it, multiply by 80 pi squared, you have the radiation resistance. To get the AC resistance, you would approximate this. You would take the length of the antenna, right? Then you would divide it by sigma of copper, probably, times the area the current flows through, and that would be simply 2 pi skin depth times radius of the wire. Y'all, I'm making sure I'm talking through this, the entirety of the problem. Got me on that? And at this point, we know just about everything except one thing that I didn't cover. Does anybody know what I'm about to do? Anybody read ahead or think ahead? Something called a beam width. This is something you're going to hear all the time. And I'm going to start over here and do beam width. And then we'll take what we did here and do it for the loop antenna, and then the arbitrarily long dipole, and after that, we'll talk about arrays. But what I'm trying to do is methodically go through one antenna and completely characterize it, and then do the next, and then the next, and finally we'll do an array of antennas and show you how that works. The whole thing with these antennas is they focus power. They put power where you want, not where you don't want. Anybody here has ever worked with a cell phone company or done anything that deals with cell phones at all? One, there's something they talk about, it's called the footprint on the ground of the actual cell phone. Really, the antennas, they're going to be the cell phone on the top of the cell phone poles, they're antennas. The footprint of the ground is they want the power in certain areas, they don't want it in other areas, it's a waste. So they get what's called an antenna footprint. Well, the antennas that do that are they're designed specifically to do just that and not waste power. That's one of the benefits of antennas. With radar, you want the antennas to literally throw out a pencil beam, almost like a laser, in scans. So when you get a reflection back, you know exactly where that target is, both the range and the relative size, right? The antennas do that. Antennas also do a thing where they do a search, and this is with radar too. They can search a space, not just to track a target, but for anything out there, and then I can identify it. Now that type of antenna is not something that's usually mechanically steered. It's electrically steered, and that's where phase array antennas come in, where they electrically steer the beam anywhere they want, and quickly. But we'll get into all that. Now, so I got to talk about beam width. This is beam width. When I talk about beam width, you always really talk about the power pattern normalized. So normally what they do for our antenna, say for the short dipole, what they actually have is this. Remember how the normalized power density was just equal to the sine squared of theta? So you get the normalized power density when you do a beam width. And this is called the half power beam width or the full power beam width, but these are just terminology. It's always with power, never with the E field or the H field, almost never. I say that, and then there's going to be some weird article in a scientific digest that looks at the E field's beam width. Most of the time we talk about power. So if I take a look at this and I just plot this versus angle. So here's my z-axis, and I'm just plotting here. The length of this line is going to be proportional to sine squared of theta. All right, so understand theta is measured from here. Are you with me? From the z-axis? Well, the sine of 0, when it would be at 0 degrees, would be 0. And it will do this. It'll come out and basically do this. Here is the point where the power here, remember the length of this line will be 1 if it's a sine. Do you follow me? The maximum length of this would be a sine. It's called a polar pattern because what you're doing is you're going to have a radius vector that's going to be equal to the sine of theta. And as theta gets larger and larger and larger, it's getting bigger and bigger and bigger until theta is 90, and then the sine of 90 is 1, and then it gets smaller, 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 down to 0 again. Do you follow me? This is called the power pattern. This would be the power pattern for a short dipole. Then there's the half power beam width. So this point would be 1/2, which would be half the power of its max, right? This point would be 1/2. And this would be the beam width right here. That's called the half power beam width. Now there's a thing called null to null beam width, but it's rarely used. Usually you're looking at the half power beam width. That's the key thing. Oh, what is the half power beamwidth for this? Well, when is sine squared equal to 1/2? That's where sine's equal to what? 1 over square root of 2, right? Where is sine equal to 1 over square root of 2? 45 degrees, isn't it? Isn't the sine of 45 1 over the square root of 2, class? So we know that this distance to here would be 45 degrees, right? And by symmetry, I could make an argument this distance would be 45 degrees, right? So that's 90 total degrees out of a total of 180 degrees. Do you agree with me? So that would be a beam width here of 90 degrees. Do you all see this? So this beam width here would be 90 degrees, and that's monstrously big. Most beam widths for antennas that are any kind of tracking antenna, target acquisition antenna, they're 3 degrees, 2 degrees or less. This is a huge swath. It doesn't really give you a lot of information. But one thing about this short dipole is, now, if you're talking about a cell phone, the old cell phones, I don't even know what the new cell phones have. The old cell phones used to have a little short dipole. That's all they had. But you think about it, it's not such a bad deal because it's broadcasting over a huge bandwidth. Beam width. Follow me? You can hold the phone pretty much any way you want. They probably had at least 2 dipoles in there. Yeah. Well, that was a short dipole, but even before that phone, I don't remember, the first flip phones that you didn't even have that thing pulled up on, it was just a little short dipole embedded in there. Does anybody know if these things are patch antennas or what in your cell? Do you know? Well, but is it in the form of a patch, or is it just, because I don't know actually. I'll find out after today's class. I want to be completely honest with you. If I don't know something, I'll tell you. And I don't know what's in these cell phones today. I think what it is, you said it's a MIMS antenna. Well, MIMS is a structure that can vary. It has actuators in it. But I think they're patch antennas in there. And they're easily fabricated. But I know it's got a broad, it's basically got a beam width that's very broad. Because if you take a cell phone, you can try this. Now, you have multiple actually points. When you turn your cell phone on and it locks up, it finds 3 or 4 towers in the area. And it prioritizes, at least I think this is the way they still do it, strongest signal, second strongest, and third strongest. And there's some, they can differentiate which one's which. Well, if ever you lose at the angle you're holding a phone, at least this is my understanding, a cell phone signal from one, it'll automatically default to the other. The problem with a lot of these things is, you know what Wi-Fi calling is, class? How many do? If you used Wi-Fi, right, then you got basically, you're going on either fiber or you're going on copper to make your call complete. You're not going right to a tower. I mean, you're going through a Wi-Fi point, which is usually just, you know, your standard type of router. But the problem is this, when you walk out, the amount of logical steps your phone has to process to go from Wi-Fi calling to cell phone tower calling, a lot of time drops your call. Has anybody ever noticed that? If you have Wi-Fi on and you walk out of a building, they're not at the technology level where they should be, where it's a handoff operation. You'll drop your call. But they'll get that solved in time too. Yeah. They're not going to have a horn in a cell phone. It just ain't going to fit. At least unless you got a phone. It might be a hybrid. They're calling it a horn. It might be a pyramidal horn.
It's a planar inverted F.
Yeah, all right. That's really a patch. That's not a true horn. All right, so now that's the beam width. Follow me? We've just characterized a short dipole in itself. We can do the same thing for what's called a loop antenna. So write this down. Now this is in your book. If you have your book, what page is the loop antenna on? Just keep flipping. 425? 445. All right. If you're following in your books, page 445. What they're going to do is this. They're going to say, I have what's called a small loop antenna. So they have this. They basically have a loop like this. They're drawing it as a circle. It doesn't have to be a circle. All right. It's a loop antenna, something like that. And the loop antenna has an area A. It's going to have a diameter D. And the key thing is D, the diameter, is much less than a wavelength. It's just like a short dipole, all right? Now, the reason they say that is this. If it's much less than a wavelength, the phase change in the current from here, if this thing is much less than a wavelength, it could be the diameter, it could be the circumference, it's much less than a wavelength. It's about the same thing, all right? Because diameter by 2 is radius, 2 pi times the radius is the circumference. That would be 2 pi times d over 2, which is just pi d. So it's about the same thing. Anyway, they're saying that this is much less than a wavelength, which means the phase change from here to here is going to be much less than pi radians, much less than 180 degrees, much less than anything that could cause a resonant phenomena to be set up there. That's the bottom line. There's no way I'm going to have something start at 0 and get a full wavelength around, come back to 0 here, and that would be a resonant antenna. They're saying it's much shorter than that. Some of this will be clear to you in a little bit, or you don't quite understand what I'm saying. But with these structures antennas, these things have something just like anything else that's made of metal. They'll have a natural resonance. At the resonance, you get a full wavelength on there, or half wavelength. Full wavelength on there, and you get a very high input impedance, which you would like. All right, that's something to keep in mind. We're going there. Not yet, though. So for this thing, Dr. Wentworth's very clever the way he words this. Normally what they do is they see, this we do in the advanced class, they'd say that's Z, and they're going to take an angle off axis theta to R, and they're going to solve for the magnetic vector potential A. Are you with me? Now, I'm not going to do this because it comes into integrals that are called elliptical integrals. Has anybody heard of elliptical? You've heard of them. My God, what class? I got to know. What's that? You've heard of elliptic integrals. Did you have Bessel functions too? You had Bessels. Did you have it or not? All right, all these things are specialty functions most engineers that I talk to, believe it or not, where you're at, don't admit to. If I'd known that, I would have done the whole thing. The elliptical function integration takes a while to do, but the nice thing is it's a closed form solution to get the fields. You get A. Once you have A, remember what happens if I get A. I'm just going to tell you this. Maybe I will do this next time. If you get A, the next thing I do is get B, right? B is equal to the curl of A, right? Right? And that's equal to mu H. And then I can go ahead and say, well, then I can get the curl of H, right? And that would be J omega epsilon times E. Therefore, I can get E. Follow me? That's how you would do it normally. I'm not about to go and delve into the elliptic integral of this thing. First off, the curl, I'm not actually sure. I would have to take this current. There would have to be an assumed current, and that's something, it would have to be assumed constant current, and then you would have to take that and project it into Cartesian coordinates, and after that you can do it, but that's an involved process. Anyway, this is what it normally goes to. You get A. I can give you A for this one, show you how to do it. Then you do curl of A, get B, and then curl of H, from B you get H. After you have H, you take the curl of H and get E. Wentworth doesn't even try to do this. He gives you A, I think, in there, doesn't he? Let me see in his book right there. He just says, even with these assumptions, this is on page 446. Solving the integral equations remains quite complicated. It's an elliptic integral and involves a pair of series expansions. He is right. There is an expansion on one of these. And some dexterous coordinate transformations. You just go to Cartesian, really. It's discovered you find A to be that. So he gives A in 859. And then he gives B by taking the curl of A. And he gets H, and then he takes the curl of that and gets E. The bottom line is this: if you look at the E field equation there, now I'm not going to ask you to do this. Just so if you're thinking about a test, what would you be required? I don't require you to derive the actual A vector potential from any of these type of antennas. I'm just saying that so you know that. All right? If I would expect that, I'd tell you I would. I don't expect it, but you have to appreciate why that's important, because it makes this derivation easier. E, it's going to give it, and in his, I forgot if he uses eta beta or mu times omega. Does he have omega here times mu for the E field?
Yes.
And it's going to be inversely proportional to R. Now, tell me what else. I know he has I here, and then he's going to have, is it pi times?
S.
I'm sorry, he has S, right? Go ahead.
It times beta
He-
over
he-
all that's over 4 pi r
Mm-hmm.
times sine beta.
Right. And here's the thing. This is the way I like doing it. Put the e to the minus j beta r by itself over r. Those are the two terms that are functions of distance. The top one's phase. R is just the distance. So that's all the information about distance right there. This is all about really everything but the current right here. This has to do with the frequency and the geometry of or the size of the antenna. S here is going to be pi a squared, where a would be the radius of the antenna. All right, then he's going to have this times the sine of theta, and it will be in the a phi direction. Now take note of that the E field's in the phi direction, and this is something I didn't state quite right yet. Here's something you always remember about wire antennas. If you have a straight wire antenna like this, regardless of whatever you want to call this direction, x, y, z, the E field will always have a component that projects onto this thing. For instance, if you look at the E field at this distance, it's straight that way, right? It's in line. If you come up here, the E field would be in this direction, but it has a projection onto that antenna. The E field would never be perpendicular to the current direction. The current direction always has, if you take the projection of the E field, it will always be in the direction of current. Now, here's the way you think about this. When charge is accelerated, the E field launch from charge accelerated is in this direction. If it's up this way, it's propagating that way, but it still has, you might say, a component in the direction of the actual current. It's not this way. Do you follow me, class? For this particular thing, since the current is swirling, it's literally in the phi direction, isn't it? The current would be in the a phi direction. Do you agree with that, if that's in the xy plane? Well, the E field is too. That means the E field here is in the phi direction. It's not in the z direction. It's not perpendicular, or a theta. Follow me? And you can see how that basically is in the same direction the current is, or it has a projection in that direction. Now that's the E field. If we want the H field, we simply take the E field in the theta or in the phi direction and divide it by eta, and then we put it in the theta direction. And that's what he has in his book there. He simply takes this value and divides it by eta. Now, something I'm going to say, people always find a way to ask this question. Are we expected to memorize this formula? No. Right? No. I'll tell you, you are expected to know the one for the short dipole, so write that down. You need to know that for the short dipole. You need to know both the resistance and the directivity for a short dipole. All right? For this type of antenna, I'm going to get right to the bottom line. You don't need to know that formula. I will give that to you. You can hold me accountable for this. All right? I will give that to you if I need it. Here's what you need to know about this. When I have these two things, and I talk about the power density, P-Av, I know it's 1/2, right? The real part of E cross H conjugated. Everybody know that, right? If we're in the far field, by the way, I didn't put this down, but all these fields are far field. This is not a near field thing. It's all far field. If you go ahead and do this, what's going to happen out here? This happened from the last one. Do you remember? Something that makes life easy. Do I need to do the E cross H, class? Anyone? If I'm in the far field, it's a propagating wave, right? What does it become? Anyone? Well, yeah. Just, that's what I'm after. Remember that. It's simply going to be equal to 1/2, right? Magnitude of E squared over eta in the AR direction. Or if you want to write it in terms of H, it would be 1/2 times eta times magnitude of H squared in the AR direction. Now that's what I'm getting at. Well, if you got the E field, you can square that thing, right? You can divide by 120 pi, and you can do it. Here's the thing I'm going to tell you out of this all this stuff. When I get this average power density, right, I can get the total power radiated. Let me just write this down. I'm not going to put in everything, but I can say P rad, total power radiated, would be equal to simply a double integral from 0 to 2 pi, from 0 to pi, of P-Av here, of theta and phi, times r squared, times the sine of theta d phi. I know I can do that. Right? It's a waste of class time to just go ahead and do this right here because you're going to see there's only a couple things that actually come out. You're going to get a sine cubed integral. The r squareds will cancel here because E or h are proportional to 1 over r. You're going to get a 1 over r squared when you square it. The r squareds go, you're really talking about a sine cubed integral again, right? Follow me on this, class? That's the only thing you're going to get. This whole thing comes down to something when you do it. For P radiation resistance, oh, I forgot the terms he puts down. I got my book too. In his book, what he's going to do is show you now he does it a little different than I'm used to seeing this. He's going to say this is equal to 1/2 times times r rad, the radiation resistance, times I naught squared. But he's going to say the radiation resistance, r rad for this antenna, is going to be 320 pi to the fourth, and then it's going to be a ratio of L over lambda squared ohms. You don't need to know that either. But that's the radiation resistance for a loop antenna. And I want to make mention of something. Remember what our qualifier was, that the diameter of the loop had to be much less than lambda? Make it lambda over 10. If you do that, if you take lambda over 10 here as the length, and then you divide it by lambda squared, oh my goodness. Isn't this the formula your book has? Oh, I'm sorry, S, my bad. And S is equal to, it's going to be equal to pi a squared, or it's equal to pi d over 2 squared, or pi times d squared over 4. And d would be the diameter, a would be the radius that you'd put in there. Anyway, this is going to be extremely small. I'm going to tell you that. If you take the standard limitations, because if d is 10th, this would be a 20th. A 20th of square is 1 over 400 pi, and that would go in there, divided by lambda squared, and that would cancel that. So then the whole thing would be squared. So it's pi over 400 squared. So pi squared over 400 squared times all that. It's going to be very small. Just take my word on it. You can do the math on this. And I put on something else. If you looked at the notes, this is for a single loop, right? I put up for multi-turns, because usually when you get loop antennas that are small in terms of the actual wavelength, in other words, they're tenths of a wavelength or less, they'll have many, many loops there. And that'll increase the antenna impedance and the radiated power. All right, so I put the formula. Did anybody see this, by the way? The formula for multi-loops up there? How many did? You did? Anybody else? Did y'all look at anything I posted? I posted the PowerPoints. Did y'all see them or not? And they had this formula, all right? I'm trying to make you aware of this. Now, that's important to know, that multi-loop thing. But I would give you the actual formula for the power. And that's the radiation resistance, and that would be the area. Now, the thing to take from this, and hear me, this is for the one-turn loop antenna. The normalized power is going to just be sine squared of theta. If you look here, the E field here is a function of theta, right? Sine of theta. The power would be the square of that. That would be sine squared theta. When we get the normalized power for the short dipole, for the small loop antenna, it's that. Follow me? Now, what do you think the gain's going to, or directivity is going to be? D max. Well, if that's the actual sine squared of theta, what else had a normalized power of sine squared of theta? Short dipole, right? Almost guaranteed this thing is going to be 3/2, and it is, because when we do 4 pi over the double integral from 0 to 2 pi, from 0 to pi of the normalized power density, sine squared of theta times sine of theta, d theta, d phi. For this whole thing, you're going to get a D max here of 1.5, and that's in the book. 1.5 or 3/2. You can prove that to yourself, but you'll get that. Now, if I seem like I don't really care about this, the formulas for this stuff, come in a variety of different things, but usually what engineers take from us, they know how to get it if they need to go through first principles. They would get A from the current, and they would do these crazy elliptic integrals and get a series expansion of them, and they would do it. They'd find A, and from A, they'd take the curl of A and get H, and then they would get E from the curl of H. They'd take the curl of H is equal to J omega mu E. You know how to do that. That's a lot of work, but it'll get the same bottom line result. And the thing you want is radiation resistance, directivity max, and the pattern, which is, the pattern is sine squared of theta. What's the beam width going to be based on what we talked about with the short dipole? What was it for the short dipole?
9.
What do you think it's going to be for this one? 90. Why? Because the normalized power pattern is the same. That tells you the beam width, okay? That's it. Now, something to be said about loop antennas. They're convenient. A loop antenna, you can wrap a lot of loops in a very small sandwich, all right? Now, many loops are usually what's used for that kind of an antenna. And it's very easy to make, and it's also conformal to most things. The problem with dipole antennas, a lot of times, is a dipole antenna needs to kind of be sticking out. Usually they don't put a dipole, they'll put a dipole and it'll be a metal plate back here and you get what's called a current image below it that will make it look like a dipole. But the thing is that they stick out, and when you embed them, like in phones and stuff like this, so they're buried, any metal next to them will interact and cause an impedance change and cause problems. That loop antenna can be pretty much a standalone thing. You can put it in the center there and put the loop in it. It will work. All right, that's the one thing to keep in mind. I don't have a lot of experience with weird-looking antennas, but I know that the loop one is a convenient thing to do sometimes. All right, now I've done that. Now we go on to the next thing, which is going to be a long dipole, or an arbitrarily long dipole antenna. We're not going to have time today to get into arrays, but we're going to get into arrays, and then we'll get into the Friss equation and then radar in a bit. Hopefully real applications. Better ringtone than mine. All right, so now we're going to talk about long antennas. All right, and these are still going to be straight wire antennas. I'll give Riggs a plug here. He has an antenna course he's been teaching for a while. If you're interested in wireless technology, radar, electromagnetic compatibility and interference compliance engineering, if you're interested in anything that deals with wireless technology, take his antenna course. It's worth it. It does a real good job of showing you from the ground up how to build them, how to design them, and also how to more or less characterize them, just based on geometries. It's really useful. Anyway, this is a straight wire antenna. So for this, we're going to have an antenna of a length L. But now L is of the order of a wavelength. Typically half wave, three-quarter lambda dipoles are typical. They're almost always center fed. They don't have the feed up here or the feed down here. It's not that you can't. Some people do that for very odd reasons. This is the way most antennas appear. Now, here's the reason this is important. This is a long wire antenna. The current has to go to 0 on the ends. Now, in our short wire antenna, what I didn't say was all that charge is going to accumulate a bunch of charge at the ends and let it go, all right? It's more or less, it's so short, that's what happens. It looks like a capacitor at a plate at the end of it. What's going to happen here is this. The antenna current's going to go to 0 there. And if we were to profile the current here versus height, this is the z-axis, this which is what you'll get. Now, depending on the actual length of the antenna and wavelengths, you could actually get this as an absolute null, where the current fed into that antenna would be theoretically zero. It's never theoretically zero. Where you could get this as a half wavelength and this as a half wavelength. That'd be a full wavelength antenna. We could also get something where it's a half wavelength, where this would be like a half wavelength. This would be the current. So what I've done here is graph current versus position. Follow me? It's just the magnitude of current. An equation for this, a general equation. By the way, this is not solvable in the general sense. This is based on a solution that's getting this continual approximation. But this I of z is going to be equal to some I naught, and then it's going to be the sine. If you look in your book, he has this, the sine of beta right there times, and he'll have beta times, I think he has L, oh boy, I forgot if he has L over 2 here. L over 2 minus magnitude of z. I think that's the one he does. There's a couple of different forms of that. Let me just check. Yeah, he has beta times L over 2 minus z, but just put minus magnitude of z. You all see that in there? It's on the current on the arbitrarily long dipole. Do you all see that in your book? He won't have magnitude. He'll have, for plus, this will be minus, and for minus, it'll be plus right there. So if that's equal to I of z, you can just think about what happens. Well, at the end of the wire, you're at plus or you're at L over 2 or minus L over 2, right? Well, that means this is 0. The sine of 0 is 0. It goes to 0 at the ends of the antenna. Do you follow me? Then based on what beta is here, you can find the value at z equals 0. Because when z is 0, you're at the middle of the antenna, and you get beta L over 2, right? So if that's what? If that's pi over 2, it's 1, isn't it, class? Right? The sine of that would be 1. But if it's pi, it's 0, isn't it? All right, when you have a full wavelength antenna, you'll get a null. You'll get a 0 current right here at the feed point. Just keep that in mind. So now if you have this as the current, and we come out a distance, I like to get rid of these kids, but I don't think. Anyway, if I come up here and I have a little chunk of current here, I have I of z at some point, and I come out a distance. Now, here's what I got to do. Hey, can you guys move for a bit? We can hear you in here. Thanks. So this is R. I'm just doing what I have to do, all right? And this is R prime. Now, hear me now. I care about this distance, because here's my current. I'm coming to come out, and I'm going to come to a point here. And what I want to do, now his book doesn't do it this way, but, well, actually, I'll do it his way. What he's going to say is he wants the differential electric field caused by this differential chunk of current. And this differential chunk of current is really I of z right there times dz, because it's going to have a certain height to it. Follow me? Iz is the magnitude, dz is the actual length. And I'm going to make that look like a short dipole. Now, I know for a short dipole what the electric field would be there. Do you all follow me? I know it would be in the far field. So in the far field, what I can say is I have dE. Now, just hear me. I know for a short dipole, it would be equal to j eta beta, right? Then it would be my I of z here. That's the I value in the z. Then it's going to be, and this is going to be I of z times dz, because it's got to have a thickness, right, or a length. It's over 4 pi, and it's really r prime, but you're going to see r prime and r about the same magnitude-wise. Then it's going to be times e to the minus j beta r prime here, and it's got a sine theta variation, and it's in the a theta direction. Now try to appreciate this. The only thing I've done is take the electric field for a short dipole. I've replaced the dl with dz and the I naught with I of z, because it's a function of the position z. So this is the differential electric field at this point here. Now something to be said is this thing right here, this e to the minus j beta r. Because r itself, if you look there, my r prime. Now take a look at this. Try to appreciate what I'm saying. These two are almost the same length. If that's r prime and this is r and we're in the far field, this total distance is much, much greater than the length of the antenna in the far field. Got me on that? Now keep watching. Here, I could say that this distance right here, the distance difference, the delta r, if you will, would really be equal to whatever this height is, z, right? It would be z, and if you look at, this is the angle, theta, right there. It would be z times the cosine of that angle. Now just think about that. If you take a look at this. When you got 90 degrees, if you're coming straight out, is there any difference in those r's, class? Not at all, right? Straight out, right? They're the same. When you're up here, then you would have a difference of exactly z. And you'll notice the cosine of 0 would be, in fact, 1, and the difference would be z. Do you all follow me? That's the difference in these paths. So what you do is here, you replace r. This is in the book. And I'll get through this a little more next time. But what happens is you replace this with now this r here is going to be the actual r measured from the center minus z times cosine of theta. Do you all follow me on that? And you can go ahead and replace this r prime with just r because it's a magnitude. Now, I know I'm about out of time, but you all see I'm going to bust this thing up. I'm going to take this and make it e to the minus j beta r times e to the j beta z cosine theta. Do you all see this? When all is said and done, here's what I get. Let me finish this thought. Now I'm going to get j eta beta. I'm going to get that divided by 4 pi r. Then I'm going to get e to the minus j beta r here. I'm going to divide that, got the r out there, thank God. Now I'm going to come over here, and I have e to the minus j, or plus j beta z cosine of theta. I have a sine of theta here, right? And I have dz here, and I want that integration. Well, I'll just tell you, if this is dE right here, what I've got, when I integrate this over dz, then I'm going to get the actual E field. That's what I'm trying to do. Go from minus L over 2 to L over 2 of this integral to get the total E field. I'll get this next time, but that's where we're going with that. We're going to get the total E field by integrating the differential E field, all right? And he shows in his book that actual integration on 868 on page 449. All right. If it's a little dry now, it'll get better very shortly.